Without engaging in a detailed analysis of categorization of separate areas, nor going into a deeper philosophical discussion, we usually hold the conception that there is one single mathematical world, which is different from, though closely related to, the real world we live in. Experience in this mathematical world can appear so foreign to daily life that many people feel turned off by it. Even though many people are aware of the utility and power of mathematics, they do not see any direct relevance of the subject to them. In both the historical and pedagogical aspects, it may be worthwhile to look at the issue in a pluralistic way from different angles. Among others, there are, for instance, a world of school mathematics, a world of tertiary mathematics, a world of daily life mathematics, a world of recreational mathematics, a world of mathematical proofs and reasoning, a world of mathematics in science and technology, and a world of mathematics in humanities. In fact, the history of mathematics affords some means to mirror these different worlds in the context of HPM to offer a fuller view of the subject, rather than like what is depicted in the ancient Indian fable of the proverbial elephant felled by the 6 blind men, though each was partly in the right and all were in the wrong. Is mathematics a useful science, a vibrant science, an amusing science, a rigorous science, a heuristic science, an experimental science, a humane science, or even is mathematics a subject in science or in arts? This lecture related to theme 4, mathematics and its relation to science, technology, and the arts, historical issues, and interdisciplinary teaching and learning, attempts to examine this issue through examples gleaned from the history of mathematics. Talking about relation to science and technology, one word naturally comes up in the mind, a popular word in the education arena these days, namely STEM. As is well known, the word STEM is an acronym for science, technology, engineering, and mathematics. Initially, the acronym was SMAC with the 4 subjects in that order. It was later changed to STEM on the ground that STEM sounds better than SMAC. However, with M placed at the end, very often one finds that mathematics has been sidestepped in most educational activities and projects carried out under the name of STEM and has been relegated to a less significant role mentioned in passing. But the history of mathematics tells us a different story. We may as well coin the word ANAP instead of STEM, which stands for 4 Greek mathematicians who make great contributions to science, technology, and engineering as well: Archimedes, Newton, Euler, and Gauss. In the Eastern world, there was a historic figure that can be mentioned likewise in the person of Shi Huangji of the Ming Dynasty, who was best known in the history of mathematics as the collaborator with Matteo Ricci in transmitting the first European mathematical text, the Elements, into China in 1607. In an official memorial he submitted to the emperor in 1629, he gave a list of the 10 categories of various applications, such as weather forecasts, irrigation, musical systems, and so on, with a remark: these 10 categories are intimately related to the well-being of the people. I learned from Jiao Bi Xuanjing what made it possible for you to set the RAM in order was Gaogu and gender. All subjects with shapes and substances can be explained in terms of mathematics. This is STEM in 17th century China. STEM, as I see it, is not a school subject, still less just a collection of high-tech products like robots and 3D printers. STEM is a comprehensive awareness which integrates different subjects so as to learn and utilize knowledge in mathematics and in science, coupled with engineering means in step with modern technology for the betterment of our lives. STEM embodies a spirit of exploration and a way of thought combined with mathematical thinking and scientific spirit to organize theories through experiments and observations in the search for knowledge and further innovation. A friend of mine designed a clever logo of STEM in the form of a keyhole which stresses the important role of mathematics. It is meaningful to look at the world of M in STEM and more generally at the multifarious aspects of the subject in relationship to other human endeavors. The American mathematician Raymond Wilder authored in his book Mathematics as a Cultural System of 1981 an evolutionary model. Let me briefly sketch a picture based on Wilder's view and idea. There are many different host cultures throughout the ages in different parts of the world. Suppose we look at one such culture, say the Chinese culture. Mathematics is a subculture of a host culture in which there are so-called internal or hereditary stress and external or environmental stress, which are respectively development in the subculture, in this case, mathematics, and the development in other subcultures, both exerting influence to and from the host culture to mathematics. And then there is diffusion to and from other host cultures. The German philosopher Oswald Spengler went even further to see in mathematics the exemplification of culture. In his famous book, The Decline of the West of 1918, he gave a comparative study of many cultures in which he noted that the histories of various cultures follow a similar pattern likened to the regular and predictable course of birth, growth, maturity, and decay of a living organism, or metaphorically analogous to the seasons. He further noted that within each culture, certain basic attitudes, which are exemplified in different expression forms, one of which is mathematics, give the key or clue to the history of the whole culture. Spengler viewed mathematics in a rather wide scope. In chapter 2 of his book, Meaning of Numbers, he wrote, "Nevertheless, mathematics, meaning thereby the capacity to think practically in figures, must not be confused with the far narrower scientific mathematics, that is, the theory of numbers as developed in lectures and treatises. The mathematical vision and thought that a culture possesses within itself is as inadequately represented by its written mathematics as its philosophical vision and thought by its philosophical treatises. Number springs from a source that has also quite other outlets. Thus, at the beginning of every culture, we find an archaic style, which might fairly have been called geometrical in other cases, as well as the early Hellenic. Gothic cathedral and Doric temples are mathematics in stone. Doubtless, Pythagoras was the first in the classical culture to conceive numbers scientifically as the principle of a world order of comprehensible things, as standard and as magnitude. But even before him, it has found expression as a noble arraying of sensuous material units in the strict canon of the statuary and the Doric order of columns. When we learn mathematics in school and university, we hold a traditional view of its method and content, comprising of theory, computation, algorithm, modeling, with proof and proving. These aspects should be seen as an interrelated and integrated whole, like the yin and yang, each complementing and supplementing the other. But even at that stage, we seem to live in three different worlds: a world of school mathematics, a world of tertiary mathematics, and a world of mathematics of daily life. Instead of going into a fuller discussion for lack of time, let me just give one simple example, that on the use of language. When we talk about conversion of currencies, we usually say something like, €1 is equal to 8.748 Hong Kong dollars. If I have E euros, which amount to H Hong Kong dollars, how will I write down an expression to indicate the relationship between E and H? Is it E equal to 8.748 H, or is it 8.748 E equal to H? It should be the latter. But isn't that look like the opposite of what we say in daily life? Indeed, this may confound many school pupils who first encounter algebraic expressions. But to go on with the learning of mathematics, we have to realize such difference in the language. 4 years ago, there appeared a paper on mathematics to be learned in school in the 21st century. I'd like to draw your attention to one remark in the paper. Our focus has mainly been on the practical value of mathematics in the world outside school. The goal of mathematics education, however, is also to prepare students for further education, to which they add the importance of understanding and appreciating mathematics as a goal in and of itself. To understand and appreciate mathematics, we cannot avoid entering a world of mathematical proofs and reasoning, which is perhaps a main cause for discouragement to most learners, because mathematical thought concerning proof is different from thought in all other domains of knowledge, including the sciences as well as everyday experience. Again, for the lack of time, I won't go into a discussion of it. However, I'd like to mention yet one more world that is less emphasized in traditional schooling, the world of recreational mathematics. Not only does recreational mathematics lead to significant mathematical results and applications in the past, as well as today, it can also be put into good use in the teaching and learning of mathematics in the classroom. In the very early days, our ancestors tried hard to survive. They collected berries and fruits, they hunted, learned to farm, to raise livestock and poultry, and cultivated the land and built their homes. They were kept very busy, but that did not mean they had no spare time. When they looked at the sky and studied the stars, astronomy began. They also played with sticks and pebbles. They counted and engaged in thinking. Mathematics began. There is a saying which is attributed to various authors. We don't stop playing because we grow old. We grow old because we stop playing. There is another saying which elaborates upon this. Cruz well says that children are young because they play, and not vice versa. And he might have added, men grow old because they stop playing, and not conversely. For play is, at bottom, growth, and at the top of the intellectual scale, it is the eternal type of research from sheer love of truth. The famous Silk Road acted as the main trade route in Central Asia that established links between a cross-cultural mix of religions, civilizations, and people of many different regions, and also enabled exchanges of learning and culture of people of different races. According to the Danish historian of mathematics, Jens Højrup, a Silk Road community of traders interacting in antiquity along this combined caravan and sea route and its extensions, reaching from China to Cardiff, and encompassing in the Middle Ages the Mediterranean Islamo-Indian trade network, with mathematical knowledge migrated through campfire riddles. Thus, we find similar games and puzzles and riddle problems in different civilizations throughout the ages. A very old puzzle attributed to Pythagoras is the stomatron. How many different ways to assemble a square from the 14 pieces? I fondly remember the first toy I had as an infant, the tangram. It probably originated from the banquet table in the 12th century Song dynasty, was in wide circulation by the 17th century Qing dynasty, becoming a popular game in Europe by the 19th century. With two sets of tangram, one can prove a special case of the Pythagoras theorem called the Gaogu theorem in ancient China. Another interesting mathematical question is to ask which convex polygons can be formed from a set of tangrams. One well-known three-dimensional analog of tangram is the Man-Keung, a puzzle the Danish polymath Pitheim created in 1936 while attending a lecture on quantum mechanics by Werner Heisenberg. There are 240 different ways to assemble the cube, disregarding rotation or refraction, obtained by hand one wet afternoon in 1961 by John Conway and Michael Guy. Here is a much simpler mathematical question. Assemble the configuration as shown. In fact, the idea of dissection and reassembling was a well-known technique in ancient Chinese mathematics, which was cleverly and skillfully employed to explain many geometric results. As one example, let us look at this recruitment advertisement in a Dutch magazine. One of the puzzles is a famous problem with a long history of transmission between different parts of the world. The original problem appears as problem 13 of chapter 9 of Jiujiang Shuanshu, 9 chapters on mathematical art. Now given a bamboo 1 jiang high, which is broken so that its tip touches the ground 3 jiang away from the base. Tell what is the height of the brick. The problem also appears with different data in the Indian mathematical treatise Bhaskara's Lilavati of the 12th century, and also in the text of the Italian mathematician Filippo Calandri of the 15th century. The Chinese mathematician Yang Hui gave his explanation of the solution in his book of 1261. In today's mathematical language familiar to school pupils, this problem can be readily formulated thus. Given A and C plus B in the right angle triangle ABC, calculate B. A school pupil of today probably solve it like this. Let L be C plus B, then C is L minus B. By the Pythagoras theorem, we have from A squared plus B squared equal to C squared, the expression 2LB equal to L squared minus A squared, so that B is equal to L squared minus A squared divided by 2L. How was it done at the time, which was more than 2,000 years ago? Note that this symbolic mathematical language that allows us to work with ease was developed as late as the 16th century, only about 500 years ago. Let us watch a clever proof without words reconstructed from the commentary of ancient Chinese mathematicians. The area of the rectangle is equal to that of the big square of side L minus that of the rectangular strip, which is A squared. But the area of the rectangle is given by 2BL. Hence again, we arrive at the expression 2LB equal to L squared minus A squared, so that B is equal to L squared minus A squared divided by 2L. Now, let me start with another riddle problem and pass on to STEM, namely the so-called Radon-Kasmas puzzle. You are given the 3 row sums, 3 column sums, and the 2 diagonal sums, all equal to 15. Fill in the 9 cells in the 3 by 3 grid with suitable positive integers, chosen from 1 to 9. One thing that may immediately come up in your mind is the 3 by 3 magic square, which is an old myth in the very ancient Chinese text I Ching, Book of Changes, the so-called He Tu, map of He, and Luo Su, writing of Luo. The Chinese mathematician Yang Hui formulated the solution, actually unique up to rotation and refraction, in his book of 1275. 2 and 4 are on the shoulder, 6 and 8 are at the feet, 7 is on the left, 3 is on the right. Put on 9 as the head, put on 1 as the shoe, 5 is at the center. But in this puzzle, we do not require all entries to be mutually distinct. There can be many solutions, like this trivial one, or this, or this, or this. There are altogether 41 solutions to the puzzle, falling into essentially 9 types, with the remaining ones obtained via rotation or refraction. There are 9 unknowns and 12 equations. Why can't the given conditions pin down the solution? Even if, in addition, we are given the 5 northwest-southeast diagonal sums, the answer is still not unique. If we are further given all the 10 diagonal sums, then the answer will be unique. In general, we are looking at a system of 8 linear equations with 9 unknowns, the rank of the coefficient matrix being equal to 7. Of the 9 unknowns, there are 7 pivotal unknowns and 2 free unknowns. The question is, what sort of condition will guarantee a unique solution if one exists? Why the puzzle is named after the Polish mathematician Stephen Karl-Marx and the Austrian mathematician Johann Radon? It is because the puzzle is closely related to their works. Karl-Marx's algorithm in 1937 for solving a system of linear equations, and the Radon inverse transform in 1917. This much is mathematics, which was later applied to medical imaging. In 1979, the Nobel Prize for Physiology or Medicine was awarded to Godfrey Hounsfield and Alan Cormack for their work in developing diagnostic technique of X-ray computed tomography. A patient is passed through the hole in a device which contains an X-ray source that rotates around the patient. As X-ray passes through the patient, it is attenuated so that its intensity is reduced to a degree depending upon what material the ray passes through, bone, muscle, an internal organ, or in the unfortunate event, a tumor. The attenuated ray is detected on the other side as collected data. Basically, we try to figure out the entries of a large grid, knowing the row sums, column sums, diagonal sums, etc. Is this mathematics, science, engineering, or technology? To achieve in science, a demand on curiosity and imagination is called for. But by that alone, it is not sufficient. Our ancestors were good at that from very early times in creating a rich store of mythology. For science to emerge, an additional demand on discipline and critical thinking with precision in mathematics as well as in words is called for. In an ancient Chinese mathematical text, Sun Ji Xuanjing, Master Sun's mathematical manual of the 4th and 5th century, we find a preface which sounds almost like mythology. Mathematics governs the length and breadth of the heavens and the earth, affects the lives of all creatures, forms the alpha and omega of the 5 constant virtues. And then it goes on and on and on. A similar sentiment was expressed in the Western world by Galileo in the Essaya of 1623. Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language and read the letters in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. Without these, one wanders about in a dark labyrinth. By adopting this view, Galileo made a significant step forward in modern science by switching the focus from trying to answer why to how much. That is, from a qualitative aspect to a quantitative aspect. To keep on asking why, we may end up in speculative discussion, but find it impossible to arrive at an ultimate source of reason. By asking how much, we have a feeling that we are in grasp of a better understanding because we can predict and carry out an experiment to check if the theory agrees with the observed facts. Philosophers would inquire further. The physicist Max Tegmark goes so far as to say, but why has our physical world revealed such extreme mathematical regularity? We'll explore a crazy counting belief of mine that our physical world not only is described by mathematics, but that it is mathematics, making us self-aware parts of a giant mathematical object. I'm not as philosophical and will not go as far as that, but I do believe that we are living in a world or worlds of mathematics. A triumphant page in history of science of the late 19th century depicted how science progressed. This page is the famous equation developed by James Clerk Maxwell with a beautiful and integrated blending of mathematics, differential equations, and science, waves, thereby unifying three physical phenomena: electricity, magnetism, and light. This page of powerful mathematical studies, supplemented with strong physical reasoning by Maxwell, was preceded by a brilliant page of experimental exploration, supplemented with intuitive and figurative reasoning by Michael Faraday, and followed by a deep theoretical investigation based on simple physical hypotheses by Albert Einstein. This triumphant page in physics of the late 19th century illustrates the standard pattern of the three stages of progress in science. From basics science to research and development, then to technology. In this case, respectively, Maxwell's equation in 1865, Kerr's discovery of the electromagnetic wave in 1886, then Marconi's invention of telecommunication in 1896. I'd like to illustrate the indispensable role of mathematics plays in STEM by borrowing from an investigation by Galileo, namely that of a projectile motion. What is the trajectory of a projectile? According to traditional Aristotelian theory, the projectile will shoot up in a straight line until the force vanishes, so that the object falls straight downward. But in reality, the projectile does not look like that at all. In the famous book, Dialogue Concerning Two New Sciences of Galileo, we find a dialogue between the fictitious characters, Salviati and Simplicio. Imagine any particle projected along a horizontal plane without friction. The moving particle, which we imagine to be a heavy one, will, on passing over the edge of the plane, acquire, in addition to its previous uniform and perpetual motion, a downward propensity due to its own weight, so that the resulting motion, which I call projection, is compounded of one which is uniform and horizontal, and of another which is vertical and naturally accelerated. Salviati then announced a theorem: a projectile which is created by a uniform horizontal motion compounded with a naturally accelerated vertical motion describes a path which is a semi-parabola. He mentioned that the ancient Greek mathematician Apollonius introduced the parabola and other conic sections and proceeded to derive some mathematical properties of a parabola required for explaining a projectile motion. You can see that by physics alone, perhaps with a little bit of mathematics in dressing up the formulation, one can arrive at a precise description of the projectile. But isn't it amazing to see that the description fits so well with some geometric object that was studied by the Greeks about 2 millennia before, namely the intersecting curve of a cone by a plane parallel to its generator? The next step in our discussion of this topic will show that mathematics is indispensable. Now that we know how to find out the range, we would like to know when the range is a maximum. As you can see, the angle of projection will change the range, and it will be a maximum at a certain angle. And by calculation, it turns out to be 45 degrees. But an athlete in shot put won't throw the shot lying on the ground, but standing up. In which case, an angle projection of 45 degrees may not give a maximum, but a smaller angle may give a maximum. And what about if you throw a ball standing on an inclined slope? Again, the angle of projection at 45 degrees may not give maximal. And you would have to do the calculation again. That requires an understanding of the mathematics involved, not just the physics. Throughout history, we witness a beautiful blending of arithmetic and geometry, or numbers and shapes. The 17th century English scientist Robert Boyle once said, "Arithmetic and geometry, those wings on which the astronomer soars as high as heaven." Are you familiar with the world of arithmetic? Having been immersed in it from primary school all the way to secondary school, most people will not feel unfamiliar with it, even though they may find it dry and are not drawn to it. Are you familiar with the world of geometry? You are living within a three-dimensional world of geometry. It is all around you, but do you feel comfortable with it? What do you see in this picture? Two triangles? Now, what do you see? Why can we depict a three-dimensional situation by drawing on a two-dimensional piece of paper? How do you interpret what you see? Light from an object hits the retina, which is like a two-dimensional piece of light-sensitive paper, which turns the light into electrical signals to be processed by your brain into a three-dimensional image you see. So we feel comfortable with our three-dimensional world. What about a four-dimensional world? See how you feel about the next question. What is the radius of a circle touching four mutually touching circles on a plane? The answer can be readily obtained through the Pythagoras theorem. What is the radius of a sphere touching 8 mutually touching spheres in space? This can still be readily obtained through the Pythagoras theorem. It looks like the same goes for the high dimensional case. Let us look at the calculated figures. Radius of the end ball touching all those end balls is square root n minus 1. But look at the figures. The end ball in the middle of the n cube pokes out of the n cube when n is larger than 9. But how can that be? Well, it is. In fact, many people, including myself, are not really that familiar with a simpler object, the four-dimensional cube, sometimes called a tesseract or hypercube. One way to visualize a 3D object is to look at its slices in 2D to piece up a picture in mind. Remember the computer tomography technique? Similarly, this can be done for an object in the n-dimensional case. Naturally, it is a much harder process. Here is how a tesseract can be visualized by its three-dimensional slices. A second way to visualize a three-dimensional object is to look at its net in 2 dimensions, again, to piece up a picture in the mind. To pave the way, let us look at the net of a cube. One interesting question is this a net of a cube? There are altogether only 11 different nets of a cube. The one given is not one. Similarly, this can be done for an object in the n-dimensional case with the net in an n-1 dimensional world. Naturally, it is even harder to imagine. The famous 1954 painting by Salvador Dali called Crucifixion provides such an illustration. The crucifix is a 3-dimensional net which folds up to a 4-dimensional hypercube. A pair of worlds closely related to the world of arithmetic and geometry is the world of continuous and discrete mathematics. The persistent tension between the two worlds fill up a long and intriguing chapter in the history of mathematics and science. The standard story goes like this. The early Pythagoreans based their mathematics on commensurable magnitudes. but the discovery of incommensurable magnitudes dealt them a blow which shook the foundation of their mathematics. An early Greek belief was all is number. What was at stake after the discovery of incommensurable magnitude was the theory of proportion, and with it, the theory of similar triangles. Eudoxus' theory of proportion came to the rescue and was written into Book 5 of Euclid's Elements. A reconstructed story from Wilbur Knorr and David Fowler goes like this. Incommensurability did not cause a foundation crisis for the early Greeks. Early Greek mathematicians worked with several different concepts of ratio, the most significant concept being that of antipheresis. In between the work of the early Pythagoreans and that of Eudoxus, there was a page of an unsuccessful attempt of the antipheresis theory. Book 2 and Book 10 of Elements contain a trace of an antitheoretic investigation of quadratic ratios. Here is a summary of this episode. Eudoxus' theory of proportion in the first half of the 4th century before Common Era led to Richard Dedekind's theory of irrational numbers in the latter part of the 19th century, while the antipheresis theory of the early 4th century before Common Era led to the theory of continued fractions in the 16th, 17th century. No wonder the Greek-French mathematician Henri Poincaré once said, if arithmetic had remained free from all intermixture with geometry, it would never have known anything but the whole number. It was in order to adapt itself to the requirements of geometry that it discovered something else. Our ancestors started with discrete mathematics, knowing only the whole numbers. Later, they came up with fractions, then irrational numbers, and moved into the realm of continuous mathematics. A turning point came when René Descartes introduced the idea of a variable, which ushered in dynamic motion and necessitated the invention of the differential and integral calculus. Then came the epoch-making contributions of Isaac Newton, making use of mathematics to explain the physical laws of nature. Put in this way by the early 18th century English poet Alexander Pope, nature and nature's law lay hid in night. God said, let Newton be, and all was light. With the immense success of differential equations, it seems that the realm of real numbers gained an upper hand in science instead of the realm of whole numbers, as in the ancient world with the Pythagorean dictum of all is numbers. However, history proceeds in a more intricate manner. 2 years ago, it was the 150th anniversary of the publication of the periodic table by Dmitry Mendeleev, in which chemical elements were classified in increasing order of atomic weights, whole numbers. Predictions and discoveries of new elements followed, as well as attempts to explain some anomalies in the initially designed periodic table. This important event in science opened up a new page in modern chemistry and modern physics, a fascinating page of Pythagoreanism with the theory of atomic structure and subsequently quantum mechanics emerging in the 20th century. It is now time to end the lecture by going back to the P of HPM, that is about teaching. Teaching is to tell a story, a good story which arouses curiosity and excites imagination. A story about the long quest by the human mind for an understanding of the world around us in all respects. At the beginning of the lecture, we mentioned the household word STEM, which has undergone several modifications. It became STEAM, with an A added for us, then STREAM by throwing in an R for reading, then iStream with an I added for information science, or SRIAM with an AI for both information science and artificial intelligence. By and by, the word will cover all subjects taught in school, but why not modify it to TEMS with an H added for humanities, which is sorely needed. With a humanistic and caring mind, and by learning from the long history of the human race, its success and failure, its rise and fall, we would breed a feeling of humbleness and tolerance. Science is not almighty in taking command of everything. Instead, we should learn how to live in harmony with Mother Nature and with others. Let me conclude with a remark I presented in a panel at the International Congress of Mathematicians 7 years ago. Mathematics is part of culture, not just a tool, no matter how useful this tool might prove to be. As such, the history of its development and its many relationships to other human endeavors from ancient to modern times should be part of the subject. Despite its importance, history of mathematics is not to be regarded as a panacea to all pedagogical issues in mathematics education. Just as mathematics, so important, is not the only subject worth studying. It is the harmony of mathematics with other intellectual and cultural pursuits that makes the subject even more worth studying. In this wider context, history of mathematics has yet a more important role to play in providing a fuller education of a person. Thank you.